All right, a couple things about air pressure before we move on that I need to say. First of all, we talk about the force of suction. Okay, or someone says, "Oh, there's a suction force that's holding something up." Technically, there is no force called the suction force, but let's explain real quickly what that is. Say you had a rubber end arrow, let's just say, or some kind of little suction cup thing that you're trying to stick in here, and here's the arrow going off this way. Okay, the end of the arrow basically is shaped something like this. All right, and there's air in here and air out here, and they put equal pressure. And as long as there's equal pressure, you can't stick it on something. But when you stick it up against a surface, this part flattens out. Okay, and then here's your arrow holding it out. All right, now there is no air pressure pushing on the inside out, so you only have air pressure pushing the suction cup on whatever it is. Okay, now as long as this is sealed and lets no air in, then it will stay stuck to it. Okay, and that's one reason why you lick it before you stick it on there. Sometimes it helps it make a airtight seal. All right, if the seal gets broken, then air leaks in the inside, and the air pressure on the inside is equal to the air pressure on the outside, and it falls off. Okay, but basically what you're doing is the air pressure on the outside, and since there's no force on the inside pushing equally out, then it stays stuck to the surface that you put it on. Okay, and that's also why it works better on smooth surfaces, because it makes a better seal and keeps that. So it's actually air pressure. Now these are called hemispheres, Magdeburg hemispheres, and basically it's two metal spheres with a seal on it. And what they did is they sucked the air out of it, basically made a vacuum. And when they did that, once again, the air pressure on the outside was pushing them shut, and there was no air on the inside to push out, so very difficult to put apart. And you can see here that, I don't know if you can see good, there's a Magdeburg hemisphere here, and there's teams of horses that they were trying to pull it apart with, and it was just extremely difficult. They couldn't even pull it apart with two sets of horses pulling in opposite directions. So very, very strong force, but it's really not the force of suction, it's really just the air pressure on the outside with no corresponding air pressure on the inside. Then it's very difficult to pull apart. All right, just kind of demonstrates the power of air pressure. Next thing we'd like to talk about is Pascal's principle. You may notice the name Pascal. That's named after a theologian and scientist in the 16th century named Blaise Pascal, I believe. But anyway, that's what we named the unit for air pressure after, in honor of a lot of his studies. But one of the things he came up with, Pascal's principle, is basically when you transmit pressure, if say we have a tube and it's enclosed, if the fluid is enclosed, and if we put pressure on this side, then that pressure is distributed everywhere throughout the fluid. Okay, we increase the pressure here, then that's going to increase the pressure all the way throughout this enclosed tube. Okay, that means it's going to increase the pressure on the sides. Okay, there's going to be pressure on the sides, there's going to be pressure pushing on this side. It's going to be everywhere, and it goes in all directions throughout, including on the other side of the tube over here. And very often we have various hydraulic systems where we push on one side and it causes something on the other side to move, because if we put pressure over here, it's going to put equal pressure over here. Now, and that's useful, but what's really useful about it is that if we put, say, 10 kilograms of pressure, which 10 times the acceleration of gravity would be 10, which is also 10, would be 100. So 100 newtons worth of pressure over here. It puts 100 newtons of pressure everywhere. But since this surface is so much bigger, it's basically 5 times bigger, it will put 5 times as much force on it, because it puts force on it everywhere along that surface equally. And so now it could lift a 500 kilogram, or that would be 5,000 newtons, because we multiply times 10 again to get the newtons. So it's going to be 5,000 newton force. So we put in a 100 newton force and we get out a 500 newton force. And so that's basically the principle of hydraulics, is that if we push on a small surface, however many times bigger the other surface is, it will multiply the effect of that. that much because it puts that same force equally throughout the new surface, even though it's bigger. All right, same general principle, hydraulics. Air compressors put pressure in a fairly small surface, which puts pressure on here, puts pressure on here, puts pressure on here, which is larger piston area up here, and so it multiplies the force of this so that we can lift up a car. Car brakes, you push on the pedal, it puts pressure on a probably small surface area, but it applies it to a larger surface area on your brakes. So if you have hydraulic brakes, that's basically how that would work also. Okay, and so that's Pascal's principle, and that becomes very useful. Now the only difference is it puts more force on here, but it moves it. You have to move this distance a farther distance, going back kind of our work formula. You have to move it a farther distance to make this one move an equal a certain distance. You have to move this one, say, 5 times as much, but it's a lot easier to put this force 10 times this force, push it farther to make a big heavy object lift up. All right. Now, other things we can talk about. Let's talk about buoyancy. All right. Buoyancy applies to air just like it did to water, objects, and air. So let's say we have a hot air balloon. This balloon displaces a certain amount of air, okay, including the basket. All this displaces a certain amount of air, but let's just talk about the balloon. We'll not worry about the basket for right now. Okay, this displaces a certain amount of air. Now, the pressure on it is less at the top because there's less air above it than there is at the bottom. At the bottom, there's more air up above it, so therefore it has a little more pressure, and therefore there's a buoyant force pushing on it from the bottom. All right, and so that buoyant force is equal to the weight of the air that it displaces. Now, will all balloons float? No. If you have a regular balloon where you just blow it up, inside is air, the same weight as the air it's displacing, plus the weight of the balloon. So when it displaces air, it's going to weigh more than the air is going to weigh equal amounts, and the actual balloon itself is going to weigh more than the air it displaces. So the total balloon is going to sink, although relatively slowly compared to, say, a rock or something else. Okay, so it's going to sink. Now, if we fill the balloon with helium, which is much less dense and therefore would weigh a lot less than the air, then the helium plus the balloon, when you compare it to the weight of the air that it moves out, it's going to be less. And so the buoyant force is going to be greater than the force of gravity on that helium-filled balloon, and it will begin to rise. Or in a hot air balloon, you have very hot air which spreads out the molecules, so there's a very low density in here of molecules. They're just moving really fast and pushing on it. Okay? But there's less and less air molecules in here, so it's less dense than the air around it, and it will lift up the balloon. All right, the last principle I want to talk about is Bernoulli's principle, and this is named after Daniel Bernoulli, which was a 18th century scientist in Switzerland. And he studied, he was a mathematician, his father was a famous mathematician, and he didn't really prove what his son was studying, but that's okay. And it worked out pretty well. Now, what Bernoulli noticed is that if you have water flowing down a stream, you have the same amount of water flowing through the whole stream. Otherwise, the stream, if there wasn't as much, then you have areas where it would either start damming up, or you would have areas where it would just get smaller and smaller. Okay, so there has to be the same amount of flow, but he noticed that the river is not the same width. Okay, if you have a wide river, and then it goes to a narrow river, the same amount of water has to keep flowing through. But in order for it to go through this narrow area, it speeds up. Okay, and so when it narrows, it speeds. So if we have a wide river, it flows relatively slow. When we get to the narrow spots, it has to flow faster for the same amount of water to get past that point. Okay, the same thing could be said for air, but we're just going to do fluids right now. Say you have a pipe, and if it narrows down to a smaller opening, either the same amount of water has to go through this pipe, and therefore it has to speed up in order for that to happen, or else it would start backing up, and that would not be a good thing, especially if it's, say, a sewer pipe or something, but we won't go there. All right, but say we're looking at this. So basically, as it gets closer together, this represents that it's flowing faster here. But the other thing that Bernoulli said is that, and this is really the whole point of his principle, not that it goes faster, but that when it goes faster, it has less pressure pushing internally, or internal pressure. The faster a fluid flows, it has less internal pressure. In other words, it's not pushing against the sides as much because it's flowing so fast this way, it doesn't have time to exert the same amount of pressure on the sides, basically. Okay? And so, for example, if there were air bubbles in the water as it's flowing, okay, over here there's less pressure. The water has time to exert internal pressure or pressure on the air bubbles, and they tend to be fairly small. But as it gets into this faster flowing water, the air bubbles get larger. Why? Because the fluid is it's moving faster and it's not putting as much internal pressure, so that allows the gas bubble to get bigger because it's not putting as much pressure on the gas bubble that the fluid normally would. Okay, so fluids that are moving, basically, that's what he's saying, are going to decrease their internal pressure, or the pressure they're putting on other things. Okay. Another way to look at this example, we've all seen tornadoes and stuff and hurricanes that talk about how it takes someone's roof off. Okay, and people said, well, the wind was moving so fast that the wind ripped it off. And if something were sticking up to catch the wind, that's possible. But usually what happens really is not. It's actually the air pressure inside the house that makes the roof come off. Because what happens is the air going across the top is flowing so fast, we know that the faster a fluid flows, it decreases the pressure that it puts, the internal pressure or the pressure that it puts on things. So as this goes faster and faster, especially as it has to go over the house and come over, which is a farther distance, so it has to go really fast, and of course you already have high winds, so that the pressure gets less and less on the outside. The pressure on the inside of the house, though, is still as high. If it's all sealed up, is still as high as it was before. It's one reason why they recommend that you open your windows so that it can equalize pressure on both sides. But at any rate, as this goes faster and faster, there's less pressure on the outside. The inside pressure pushes up, is greater, and so it basically pushes the roof off the house. Okay, and it's because of how fast the air is flowing on this side that it exerts so little pressure that the inside air pressure pops the roof off, really, and pushes it out from the inside. Okay. Another principle of the same thing would be basically airplanes, flight of airplanes. Airplane wings are usually curved across the top and flatter across the bottom. So basically, for this air, or you can think of it as the air flowing over the wing or the wing moving through the air, either way, it's still going to increase the flow over it. Now, the bottom is flatter, so it's more of a straight line. On the other side, it has a hump, so it has to go up and down, which means it has to flow a farther distance to end up on the other side of the wing over here. That means it has to, if it's going farther and has to get there in the same length of time, that means it has to go faster. If it goes faster, then it does not exert as much pressure. That decreases the pressure on the bottom of the wing, and you still have the greater pressure on the bottom of the wing. The top of the wing has less pressure. Sorry, I may have said that wrong. And therefore, since there's less pressure here, there's more pressure here, so you get a lift. We talk about lift of a wing. Well, that's basically what supplies the lift. Okay, and that is the higher pressure here. Now, of course, you also have to have the power of the engine pushing it forward, and you have air resistance to drag. That has to do with the forward and back motion. But the up and down motion has to do with the flow of the air. It has to go a farther distance over the top of the wing, so it goes faster, and therefore it has less pressure. The bottom has more, and this gives you lift, which allows the airplane to get up. The same general principle is responsible for a curveball. As the ball curves, okay, it creates a flow of air, and basically you end up with less pressure on one side, which causes the ball to swerve up or down or to the sides, and this is what gives you curveballs and sinkers and things like that. So a very similar type of instance. Now, a couple problems real quick to think about. If you have this situation where the umbrella poofs up the other direction, what does that have to do with Bernoulli's Principle. Think about that, and maybe we'll talk about that on Thursday. All right, that'll do it for fluids.